Okay, let's look at another charge distribution problem together. This problem is still just a one-dimensional distribution, but it adds complexity from the last problem that we looked at. So kind of take the problem in. We have a uniformly charged rod again. Our total charge is negative Q this time. So it's charged uniformly. The total charge is negative. And we're given the length of the rod. And this time we're interested in a point that's off to the side of the rod, some distance A, right? And we're interested in the electric field at that point. So we know that the equation that we're starting with is the equation, the E field due to a point charge. So KQ over R squared. And that's our given equation for this scenario. And we know that we need to write that as a differential. So we need to write that as dE equals K dQ over R squared. So that'll be your job to make that transition when you're solving this problem, because I wouldn't give you the equation in a differential form. I give you the equation in the discrete form here, and then expect you to change that into a differential form. So this problem, I like it. There are different ways to solve it, and that's really what I want to focus on with you right now is some going through some options. So the first option that I think I'll have us go through is coordinate system option of placing x equals 0 at the left end of the rod. So let's start with that. So let's start with having to the right be positive x here. And we can say upward is positive y. And then this right here is our x equals 0. So we're really clear about where our origin is. We always have to be clear about where our origin is. Hopefully you remember from the last solution why that is the case. So we have a sign convention, we have an origin, so that means that we have our coordinate system in place. All right, now let's go through all the different things that we need to define. We remember that we need to define dq. And this is a line charge, so we're going to define it in the same way that we did last time, where we have dq equals lambda dx. And now I'm going to pause and go in and draw in the dq, which is something that I always want you to do as well. And so dq is just a little point charge. It's a tiny, tiny little piece of charge in my charge distribution. This is a one-dimensional distribution. Just keeping, I know I'm drawing as kind of two-dimensional chunk, but really this is a line charge, so it's one-dimensional. So this here is my dq. And then I can also call that, let me switch out colors. That also, that same piece there has some length to it, dx, right? So also dx. And x, remember how x is defined is from the origin where x equals 0, measured to my differential element right there. So this distance in here is x. So you can see that x changes by dx as we move along from point charge to point charge along this distribution. All right, cool. So we've defined dq. That was not a big surprise. We did it the same way we did last time. We need to define r. So in this case, now I'm going to go in and change colors again to draw r in a different color. So remember, x is always defined as from the origin of our coordinate system to the differential element, and r is defined as the distance from the differential element to our point of interest. So r is this distance right here. Right here. R is not a vector. So it has arrows on both arrowheads on both sides. I'm just spanning that distance in there R. Notice that when I write out X, it only has an arrowhead on one side there when I'm indicating that in my diagram. So I'm showing that X is going from the origin and pointing toward, right? the position, pointing toward the position of my differential element. So I have x, I have r, cool. Now let me define r in terms of x, and this is where I tie my coordinate system into the theory. So the equation of electric field for a point charge is very pure, kq over r squared. It doesn't have anything to do with the coordinate system. The coordinate system is an artificial layer that we place onto the problem in order to help us execute what we need to do. So we have to tie r and x together. That's our job when we define r. So in this case, let me look at r, how I can define that. So have a look at that for just a moment on your own. Think about how r will change. Always move that differential element around in your brain and make sure that that everything you're defining is robust, that you're not going to break anything by moving that differential element around. So notice what happens there. What I end up having as I move the differential element around, right? I can see that what r is equal to is equal to the distance L plus A minus x. Can we see that? Yeah, so that's my definition of r. So I have dq defined, I have r defined, and then surviving component, we need to pause for a moment and think about cancellation. So I would ask myself here, is there any cancellation? Do I need to worry about a surviving component? So my surviving component, and all of it survives, right? So there's no cancellation. I'll let you think about that, and let's draw in our DE because I didn't do that. So our DE, that's of course the contribution to the electric field from DQ. Now remember that DQ is negatively charged. So my DE is going to be right in here. It'll look like this. Now in this problem, we are only interested in the electric field at point P. Nobody's asking us for the electric field at any other point. So a common error when students are solving this is they draw in DEs at other places. And for me, that's kind of maybe missing what the problem is asking. So the problem here is asking for us to determine the electric field at P. We are not analyzing any other point in this problem. All right, so cool. We have no cancellation, so we don't have to worry about like making a component, creating that and expressing that at all. So that means that we're pretty much ready to go with this. I'm going to make myself a little bit more space here. So I'll just say cancellation. No. No cancellation. All right. So what that means is that I'm considering all of the electric field. So the electric field at P, right, is going to be equal to the summation of all of my DEs. There's no sine theta or cosine theta or anything there. I know I'm adding them all up because every DE, they're all going to point to the left. So think about it. From every DQ, right, they're all going to point to the left. So why are we integrating? Because they're going to have different magnitudes, right? Every DQ is a different distance from P. Distance matters. We have the r squared in the denominator of our equation. So that's why we have to integrate. If everything's exactly the same, obviously, you don't even need to pull any integration. All right, let's write out our integral then. So here I'll have my k dq, that's going to be lambda dx, over r squared. So that will be L plus A minus x squared. And I'm going to integrate that from 0 to L. We always go from low to high here. And as I'm choosing the bounds of my integration, I look at what I'm integrating with respect to. In this problem, it's x. So I know I'm starting my summation at x equals 0, and I finish my summation at x equal L. All right, I'm going to leave the actual integral to you.